Okay, so by now you could have worked, yeah, it's just garbage. Okay, so f prime of x is 6x plus 2. F double prime of x is 6. What does that tell us?
Concave up.
Since f double prime of x is greater than 0, the graph is concave up, right, for all x. Okay, so yes. Okay. All right, next. Discuss g of x, which is equal to x to the fourth minus 4x cubed minus 18x squared plus 5x minus 1 in terms of concavity and points of inflection. Okay, which means we got to go get the second derivative, right? Second derivative is going to tell us whether it's concave up or concave down based on whether it's positive or negative. Also, what happens when it's 0. Well, let's take a look. So, go ahead. You can do the first two derivatives for this, right? I mean, you don't need me for that. And that's where I'm writing. Oh, let me kill it now. Okay, and then you want the second derivative, right? Okay, so what do we want to do with this, right? We want to find the zeros, and then we want to find where it's positive and where it's negative. So we know that that's a parabola. We know it opens up. We know it has some roots because it's going to factor nicely. And so it's, going to look like this. It's got areas that are positive, and it's got a chunk that's negative, and we got to find all that out. So we're going to start off by finding where the second derivative is 0, and then work our way through. So next page, yeah. Okay, so set all right, so it's going to be 12, and what do we got? X squared minus 2x minus 3. Okay, so we got 12, and then x minus 3 and x plus 1, right? X squared plus x minus 3x. Yeah, minus 2x minus 3. So we have zeros when x is equal to negative, or sorry, x is equal to 3. So let's go through our interval analysis, right? We'll take a look at some intervals. How will we do that? Room here. And I'm not going to squish it. Let's go down. Hang on.
Is that an X or a 0?
It's an X. Look,
0 equals.
that's what happened, right? It's technology. If I don't lift the pen, I'm okay. If I lift the pen, I'm... All right, so what do we want? We haven't... It just bugs me when I'm writing there.
I think we just need to calibrate it.
Sure, let's do that. We can even record the calibration, but it's not going to work. If we have learned nothing by now, it's the calibration does not affect this. Okay, no difference. Oh, wait. All right, never mind. So one-time calibration. All right, you were right.
I'm so glad that was on video too.
Yeah, I will post it on YouTube. It'll be there. All right, what do we got? We got x is less than -1. So we got 3 intervals, right? We have 3 factors. We have 12. We have x minus 3. We have x plus 1. We have f double prime of x. And then we have what's going on the interval, right? Okay, so 12 is just 12. That's always positive, really. Doesn't even enter into things, really. X minus 3. So when we subtract 3 from some negative number, which is this, x is less than -1, this will be negative. And when we have a number that's less than -1 and we add 1 to it, it's going to stay negative. So that the factor, right, so the second derivative will be positive. And that means that it will be concave up on the interval from -infinity to -1. Concave up, so you draw it so that it holds water. From -1 to 3, that's positive. So x is less, or sorry, we're subtracting 3 from that, so that's going to be negative. We're adding 1 to something that is, already greater than -1, so that will be positive. And this will work out negative, and it will be concave down on -1 to 3. So on that interval, we'll have concave down. Right? So we're looking at this. And when x is greater than 3, it's all good. It's all positive. And then we're concave up on the interval from 3 to infinity. Now, if we're going to go from concave up to concave down, what happens? Where does that happen? Where do you go from concave up to concave down? It's called the point of inflection, right? So then we know that there will be an inflection point at -1, and there will be another inflection point at 3, right? Because we're changing concavity, right? Concave up to concave down at -1, concave down to concave up at 3, okay? So since we change concavity at -1 and 3, these are points of inflection. Since we change
So will the factors generally always be points of inflection?
Could be. Yeah, in general, most of the time. Let's say most of the time. It's like most of the time critical numbers are max or min, right? Not always. Okay, but a good chunk. Since we're changing concavity -1 and 3, these are points of inflection. All right, so we have met the criteria, right? We have discussed it in terms of concavity and points of inflection. Okay, last example. Right, this is going to foreshadow. I'm going to change things just a smidge. There's a couple of things in there that, you don't have room to do this on the paper, right? Like, there's no way. So you need to be doing this on a separate sheet of paper, okay? Because here, it took me this and this, so you're not doing it in the spaces allowed. I guess you could flip to the back of the you could,
That is the back.
Oh, for you that is the back, so never mind. Don't flip to the back, because that is the back. It's just not a good week. I don't even see that. All right, so I'm going to do this just a smidge differently.
Oh. Wait, are they gonna open three?
Okay, so here's what we're going to do. Basically, what I'm going to do is do the curve sketch. We're going to do the full-blown curve sketching that we're going to do tomorrow. and henceforth and forever. So we're going to follow the points in the book. It's just a couple of more things that that I'm going to do up here than are in here. Okay? And we're just basically going to follow the book on curve sketching. So we have f of x is x over x squared plus 1. And so here's what we're going to do. So we're going to start off with A. We're going to find the domain. So what's the domain of this function? X belongs to reals, right? Because you look at the bottom and you say it's x squared plus 1. Well, that's always positive, right? So we can't get this to be 0. We can't get this to be undefined. So x belongs to the reals, right? That's important to know if you're sketching, right? It's like, well, you know, are there asymptotes anywhere? No, because, right, the domain is all real numbers. Second thing we want to find is intercepts. So this whole AB, and I'm going to go up to H, that's what the book does in the next section, not the next, but the next section on curve sketching, right? A, find the domain. B, get the intercepts. Okay, what's the intercepts? Well, how do you get intercepts? You get the y-intercept by setting x to 0, right? So y-int set x equal to 0, which leads to what? 0 over 0 squared plus 1, which is 0. So the y-intercept is 0. Well, so is the x-intercept, right? So the intercept is 0, 0. There is only one intercept, and it is 0, 0. But if you're going to sketch a graph, you need the intercepts, right? I need all of the x-intercepts, all of the y-intercepts. So that's B, intercepts. C, now we do symmetry. Okay, and I think that was the first thing on the worksheet, but now we're going to do symmetry. So, if you remember symmetry, f of negative x, so symmetry, if f of negative x is equal to f of x, then that's even symmetry, right? Which is just a reflection in the y-axis. So like a parabola, you know, that was just centered. And if f of negative x is negative f of x, then that's odd. Okay, and odd symmetry is a rotation around the origin by 180 degrees, or it's reflect in x and reflect in y. I mean, same result. Okay, so what do we have to do? Basically, you're going to have to do f of negative x, right? When you want to find symmetry, you do f of negative x. Okay, so we need, we need to evaluate f of negative x, right? And then we'll see, well, is it f of x? Is it just the function, or is it the negative of the function? Okay, so f of negative x is negative x over negative x quantity squared plus 1. Right, so all we're doing is substituting negative x in everywhere we see x. And that's negative x. Negative x quantity squared is just x squared. And that's the negative of x over x squared plus 1, which is negative f of x. So we have odd symmetry, right? Okay, so now we know the domain, right? We can sketch this without lifting our pencils. Right? The domain is x belongs to the reals. We have an intercept. We know we have to go through the point 0, 0. So that's one of the things. When we go to sketch this, we can say, all right, we got an intercept at 0, 0. Okay. We know that it's got odd symmetry, which means if we sketch the right-hand part of it, we know the left-hand part is just from 180 reflection, right? And hang on, I'm just going to move. Okay, next thing we're going to do, D, asymptotes. So you need to figure out if there are any vertical asymptotes or horizontal asymptotes. So we know there are no vertical asymptotes, right? Because the domain is x belongs to the reals. So vertical asymptote. Okay. And you know, just just say since x squared plus 1 cannot equal 0, there is no vertical asymptote, right? Horizontal asymptote. Well, this should be fresh. We'll take the limit as x approaches plus or minus infinity of x over x squared plus 1, which is the function. To get a horizontal asymptote, we divide by the highest power of x, which is x squared. Which gives us limit what do we got? 1 over x over 1 plus 1 over x squared. And we can now do our limits, right? So the limit as x approaches infinity of 1 over x is 0 over 1 plus 0, which is 0. So we do have a horizontal asymptote of y equals 0, right? So HA, y equals 0. Okay, so we're doing A, B, C, D, E, F, G. 7 things we're going to go through, right? And we're halfway through. Right? I mean, the 8th thing is just sketching it. So we got to figure out the domain. Then we want to figure out the intercepts, symmetry, asymptotes. Next thing we're going to do is go to intervals of increase or decrease. Okay? And all that's doing is basically just using the first derivative, right? First derivative is positive, it's increasing. Negative is decreasing. So E okay, so we need this to help us sketch it, right? We know whether it's increasing or whether it's decreasing. Okay, am I drawing up or am I drawing down? Okay, so let's just say f of x is x over x squared plus 1. F prime of x. It's been a while. I don't know how you do this stuff. Take time off, right? So it's what? X squared plus 1 times 1. So it's the numerator times the derivative of the denominator minus the denominator, or sorry, the numerator times the derivative of the denominator over the denominator squared. So what do we got? X squared plus 1 minus 2x squared. So what's that? 1 minus x squared? All right. So we're partway there. We've got the first little bit, right, which is just getting the denominator. What we now need to figure out is, when is the denominator greater than 0? When is it less than 0? So what's the critical part of the denominator? What are we looking at, the numerator or the denominator? What's the denominator always? It's always positive, right? So we don't need to look at it. We need to look at 1 minus x squared, right?
Could be a difference of squares.
That is a difference of squared. You're right. Okay, so let's work that out then. So what are we going to say? Let's go to a new page here. So f prime of x so f prime of x is greater than 0 when 1 minus x squared is greater than 0. So what do you want to do? You want to factor that? We can just do the 2 factors and then say, look at the cases, what they both have to be, whatever. So 1 minus x squared is greater than 0 when this, 1 minus x times 1 plus x is greater than 0. Okay? And you know what our critical numbers are 1 and negative 1, right? So we have an interval of below 1, between -1 and 1, and greater than 1. I mean, there's a number of ways you can do this too, right? You could just say, oh, it's a parabola that, you know, does this. And okay, so where are we? Right, so let's do the case. If that needs to be greater than 0, then that means that 1 minus x has to be greater than 0, and 1 plus x has to be greater than 0. Okay, so that means that negative x is greater than -1, which means that x is less than 1, right? So if x is less than 1, this thing is going to be greater than 0. And what will this be? X is greater than -1. So we need both of these things to happen. At the same time, it's got to be less than 1 and greater than -1. Okay, which puts it between 1 and -1, right? So between 1 and -1. Or between -1 and 1. Or, what else? 1 minus x can be less than 0, and 1 plus x. So their product will be positive if they're both less than 0, right? So this product is positive if both of these are greater than 0, which happens in this interval, or if both of them are less than 0. Okay, so we've got negative x is less than -1, so x is greater than 1, and x is less than -1. So it's got to be greater than 1 and less than -1, which it can't really do at the same time, right? Okay, so then the first derivative will be positive in the interval between -1 and 1. Okay, so let's summarize that then, right? What do we got? So, what did we say? So f is increasing on this interval. And f will be decreasing on this interval, right? So we're increasing from -1 to 1. F is decreasing. That's f, the original function, right? So we go to sketch it, we say, okay, it means I need to be going up when I'm going from -1 to 1. Okay, otherwise I'm going down. Okay. Next thing we want to find, local maxes or mins. Okay, so local maxes or mins. We'll go to another page. That's F. Okay, well, looking at part E, which I just got rid of, and the first derivative test, then if we say, so if it's decreasing and then it's increasing, then there's going to be a local minimum at -1, right? It's decreasing to -1, then it's increasing, so we're looking at this situation, so there's a local minimum. And then it's increasing and then it's decreasing, so there'll be a local maximum at +1. Okay? So using this result and the first derivative test, we know that we have a local maximum, decreasing, we have a local minimum at -1, local maximum at +1. Okay, so let's do that. So using part E and the first derivative test, local minimum when x is -1 and f of -1 is going to be -1 over -1 squared plus 1. Okay, so we got a local minimum at -1 and -1/2. Okay, and then local maximum when x is equal to +1. So we need to evaluate the function, right? Because we need that value. We're going to plot that and say, okay, here's my min, here's my max. Okay, so f of 1, which is +1/2. So local maximum at 1 and 1/2. Okay, so we're building up all of this information, right? Which we're then going to eventually put together and say, okay, now we can graph this thing. Concavity is next. Concavity. So that's what we just learned, right? That's G. So we need to know where is it concave up and where is it concave down, right? Which is also then going to give us the points of inflection, right? Because where it changes from concave up to concave down, then we know, oh, and there's a point of inflection there, right? So all these points are stuff we need to draw this graph. Okay, so concavity, we know that f prime of x was what? 1 minus x squared over x squared plus 1 squared. And we need f double prime of x. All right, another quotient. So what have we got? We've got the denominator times the derivative of the numerator. Okay, so denominator times the derivative of the numerator minus numerator times the derivative of the denominator okay, so derivative of the denominator is 2 times this, and then the derivative of the inner function chain rule, right, times 2x, all over x squared plus 1 to the 4th. Okay, and now we're going to simplify this, right? Hopefully it simplifies, because we have to work with this. So I have an x squared plus 1, I've got an x squared plus 1, I've got a 2x. So we've got a common factor we can pull out of 2x and x squared plus 1. Okay, so let's do that up top. So we're going to pull out a 2x and an x squared plus 1. So this first term, well, it's got a negative, and then we need one more of these. So it'll be negative x squared plus 1. Okay, so now that is that. Minus, okay, the 2x is gone, and this x squared plus 1. So we've got 2 times 1 minus x squared. Over this. Ooh, actually worked. So something in here has got to simplify, right? So let's do that. So 2x, as a matter of fact, let's take this out, make that a cube, right? Those guys are the same, so this can go into this, and we'll get a cube on the bottom there. So x squared plus 1 cubed, and what have we got here? So we've got negative x squared minus 1 minus 2 plus 2x squared. So that's going to be x squared minus 3 and here we go. Huzzah! The second denominator. Sorry, second denominator? Yeah, sure. The second derivative. Second derivative. So we need to know where it's positive, right? Because positive is concave up, negative is concave down. And what can we say about the denominator of this? It's always going to be positive, right? Because whatever x you put in there, just look at the denominator. You square the x, so that's positive. You add 1 to it, and then you cube it. Denominator is always positive, so it's the numerator we're going to look at, right? We're going to say, all right, what's critical? Well, if x is 0, then, so that's one of our splits for the interval. So the denominator is positive. So the numerator is 0. Either when x is 0 or x squared minus 3 equals 0, which means x squared is equal to 3, which means x is plus or minus root 3. So we've got 3 values to look at, right? Which means 4 intervals. So we've got 0, negative root 3, 0, and positive root 3. So we're going to be looking at 4 intervals. Below negative root 3, between negative root 3 and 0, between 0 and positive root 3, and above root 3. Okay, so to do that, we're going to set up a little chart here. So x is less than negative root 3 to 0. Why am I drawing? 0 to root 3. Okay, and what do we got to look at? We're going to look at the factor 2x. We're going to look at the factor x squared minus 3. Those two factors together give me the second derivative. And that tells me information about the original function, f. So, if x is less than negative root 3, it's a negative. This will be negative. If it's less than negative root 3, then when we square it, we're going to get a number bigger than 3. So this will be positive. The second derivative will be negative, and the function will be concave down on that interval. So the interval being negative infinity to negative root 3. Between negative root 3 and 0, so you pick a number like negative 1, this will be negative. This is negative 1. It's like 1 minus 3, which is negative 2, so that will also be negative. That makes the second derivative positive, meaning that on this interval, from negative root 3 to 0, it's going to be concave up. Between 0 and root 3, pick a number like 1. So this is positive, 1 squared minus. That'll make that negative. This will be negative. It'll be concave down on the interval from 0 to root 3. And greater than root 3, that's positive. That's positive. That's positive. And we're concave up on the interval root 3 to infinity. Now, since there's changes in concavity, what happens when the concavity changes? We have a point of inflection, right? What's the second derivative at that point? 0. So when the second derivative is 0, you've got points of inflection, right? And there may be a change in concavity. Okay, so what are we going to say? Since with concavity changes, at plus or minus root 3 and 0, there are 3 points of inflection. Okay, and those are, so we've got negative root 3, and what was the original function, right? It was like x over x squared plus 1. So it's going to be negative root 3 over 3 plus 1 is 4, so that'll be negative root 3 over 4. 0, 0, right? We already know that the point 0, 0 is on there. Remember, it's our intercept. And then the other one will be positive root 3. So root 3, this will be 3 plus 1 is 4, so root 3 over 4. Okay, so we got everything we need, right? We have points of inflection, we got local mins, local maxes, intercepts, all the good stuff. So we should be able to go sketch this. So put all the information together. So H is sketch. Okay, so we got an intercept at, let's go back through and look. We've got an intercept at 0, 0. We know there's odd symmetry, but we can still sketch this without really knowing that. There are no asymptotes. We have a local min at -1, -1/2, and a local max. Okay, again, that's symmetrical, right? That's a rotational symmetry. At this point, it will rotate onto that point. What else do we have? We have inflection points at -√3 and -√3/4. So that -√3 is somewhere further out here. That's the minimum. So there's going to be an inflection point like here, another inflection point here, and this is also an inflection point. Okay, we're concave down. So as we come to here, we're going to be concave down. We are also, based on the intervals of increase or decrease, we are decreasing on negative, and so we're decreasing to here. And then this. And then this. Okay, so we're concave down, we're concave up, concave down.
Horizontal asymptote and y = 0?
Yeah, so that's why this should go
How
along
does it
here,
go through the thing?
and this should come here.
It's still allowed to go
You're allowed to go through. So the asymptote is what's happening at the extremes, right? What's happening going through the asymptote. You can pass through an asymptote. Okay, it's what the asymptote is. Remember, what do we say? The limit as x approaches infinity or negative infinity of this is 0. Okay, but here you are allowed to go through an asymptote line. So that's in theory what it should look like. Let's pause this and then go graph it and see if that's what it looks like. So. How do I pause? Okay, so there's our graph. There's maxes and mins and intercepts as shown on the graph. So if you're going concave down, you're changing to concave up. So there's going to be a point of inflection here as well as here as you're changing from concave up to concave down. Limit as you're going to infinity, 0. So it all looks good. All right, let's throw one more thing in. Second derivative test. So another application. So second derivative. We know if the second derivative is 0, then we should have a point of inflection there, right? It could be a change in concavity. We can also use the second derivative test to test for maxes and mins, right? So the second derivative test. Can test for maximum and minimum values. So here is the second derivative test. So suppose the second derivative is continuous near C. Okay, so some value. So there's two things. If f prime at c is equal to 0. If we have a critical number, remember when the first derivative is equal to 0, that's a critical number. And if you evaluate the second derivative at that value, if it's greater than 0, then it says that it's concave up, which means at that value we must have a minimum, right? So the second derivative. So if the first derivative, we have a critical number at the first derivative, and if the second derivative is positive, right, greater than 0, then it's concave up at that point, which means that f has a local minimum at c. And f has a local minimum at c. If f prime at c is equal to 0, so again, if we have a critical number, just coming to check out.
Just want to see if you're teaching them concavity right.
Yeah, you're being
You
recorded,
may
just
or
so
may
you
not,
know.
you may or may not know.
Oh, okay.
Here are my keys. My smartphone was all messed up earlier. And that. You're around Thursday, Friday, right? 3 or 4 weeks ago.
I will.
Okay, so what's going to happen is, I'm not here Thursday, Friday because of robotics, so I will have a sub. I don't know how much calculus they'll know, but this guy knows more than any of us put together, because he's been teaching it for 100. He's retired now, but
Except if you come from Korea
oh.
last year.
At
You
which-
know more calculus than I do.
At which point, yeah, all bets are off.
I like you wouldn't think like you're Korean.
Are you gonna edit this video or not?
What's that?
Are you gonna edit the video? Or
No, it just goes up. Nobody's ever going to watch it, so what's there to
Okay.
There is the one I did have to edit some words out of one. If f prime at c is equal to 0, so if we have a critical number and the second derivative is less than 0, it says that it's concave down, which means that we have a maximum. Okay? That should say then f has a local maximum at c. Okay. Here's the plan. We're just going to do one example of this. Tomorrow we will do curve sketching, right? And then the rest of tomorrow, Thursday, and Friday will just basically be a chance to work on all of the stuff, right? So I will be here tomorrow. Then Thursday, Friday, if there's any difficulties and the sub doesn't know the calculus, right? Then he can call Mr. Kader and he'll come down and give you a hand. Okay? So I won't leave you hanging. Okay, so here's the example.
I think they gave us a handout. No, it's still gonna say it's gonna be like it doesn't make sense why it's
Okay, so this time we're going to do an abbreviated curve sketch. We won't go through the whole rigmarole, right? We'll save that again for tomorrow. Okay, so we got the curve x to the fourth minus 4x cubed. We want to talk about concavity, points of inflection, local maxes and mins, and then see if we can come up with a sketch, and then we'll pop into Desmos and see if that's what it actually looks like. Okay, so well, at least this is easy to find the derivatives, right? So then f prime of x Okay, so we got f prime of x, which is 4x cubed minus 12x squared. Put that in factored form because we've got to find the zeros, right? And f double prime of x is equal to 12x squared minus 24x. And we can factor that as well, giving me what? This. Okay, so nice and easy. Right, much easier than the last one, finding the derivatives. So to find critical numbers, we're going to set f prime of x to 0, right? Which means that the critical numbers are 0 and 3. Okay, so let's do that. Okay, so to find the critical numbers. So x equals 0 and x equals 3. Now, what we want to do now is use the second derivative test, right? At 0 and 3. Okay, so to use the second derivative test,
Yeah. This is where
and f double prime of 3 is 9, 108 minus 72, which is 36. Okay, so we have some information from the second derivative test, right? Well, one piece of information, this one here. So the second derivative test is telling us that since f prime of 3 is 0, which is a critical number, and f double prime of 3 is greater than 0, then f of 3 is a local minimum. Okay. So since f prime of 3 and f double prime of 3 is greater than 0, then f of 3, which is what? We got to work out f of 3, so that's 381 minus 27 times 4. Well, 81 minus 3 is negative 27. Is a local minimum. Now, since f double prime of 0 is equal to 0, the second derivative test doesn't give us any information for this. Second derivative test. But since f prime of x is less than 0 for x is less than 0, and also for x is between 0 and 3, the first derivative test tells us there is no local maximum in there. Okay, so the first derivative test tells us there is no. There is no local maximum, no local maximum or minimum. At 0. And actually, it's telling us, actually. It's actually telling us that. Decreasing to the left of 3 and increasing to the right of 3. Okay, and you get that by the signs that will be on this, right? Left of 3, this will be negative. Right of 3, this will be positive. Okay, there's more. Let's just finish this on. Sure. Leave that for a minute.
Today, tomorrow.
So Matt, you'll get your 2 work periods, they'll just be delayed a little bit. So tomorrow we'll do curve sketching, which we would have done Thursday, then Thursday, Friday will be 2 work periods. Okay, so you'll have a chance to get lots of work done. And I'm going to try and find somebody who knows calculus, but they can be tough to find, but Kader is here and he'll help out period 4 if need be, right? Okay, so, oh, hang on, let's go back. So if we want to look at, concavity, then we're going to look, we got 0 and 2, right? So we're going to split the number line up into less than 0, between 0 and 2, and greater than 2 to see if we're concave up or concave down. We already know, and we have found the local minimum. And then let's see what else is going on and be able to come up with a sketch of this. Okay, so again, we have the interval. X is less than 0, between 0 and 2. X is greater than 2. I don't need this. We have 12x. We got x minus 2. Okay, so when x is less than 0, this will be negative, this will be negative, this will be positive, this will be concave up to 0. Between 0 and 2, this will be positive, this will be negative, this will be negative, so it's concave down on 0 to 2. And greater than 2, this is 2. No, this is positive. This is positive, this is positive. We're concave up on 2 to infinity. So 0, 0 is an inflection point, right? because you're going from concave up to concave down, and the point 2, comma, whatever, what's 2? 2 to the 4th minus 2 to the 4th, 16 minus 32, so it would be 2 negative 16, right? So we have inflection points at 0, 0, and 2 negative 16. Okay, concave up, concave down. So we should be able to sketch this now, right? All right, so we've got an inflection point here, an inflection point at 2 negative 16. We've got a minimum at 3 negative 27. That's going to go up there. Up. Change it there. So we have inflection points. We're concave up, concave down, concave up. So that's 0, 0. This is 2, 6, negative 16. That's 3, negative 27. Okay, so we use the local minimum at 3, negative 27, the 2 inflection points, the concavity, right? All right, so today you can do anything from this section or the next section. And then tomorrow we will do curve sketching, and then Thursday, Friday will be work periods, and Mr. Kader will be around to lend a hand if I don't have somebody that knows the calculus.